Welcome back to the deep dive. Today we are tackling something that is absolutely fundamental to network stability, but it kind of operates completely in the background. We are talking about the Spanning Tree Protocol, STP.
It's arguably one of the most important safety nets in all of networking.
Okay.
It has to exist, really, to solve this major paradox.
Which is?
Well, you want backups, right? You want redundancy. That's a good thing. But the physical act of creating that redundancy, if you do it wrong, can cause, and I mean instant, catastrophic failure.
And that is our mission for this deep dive. The source material we have gives us a really clear path to understanding this, from the basic logic of how it works to the huge difference between the old slow version and the lightning fast one we use today.
Right. We want to make this super simple for you.
So let's start with the problem, the core conflict.
The challenge really starts with a good intention, a very human instinct. You've got switches, say, connecting different floors in a building, and you think, okay, if one of these cables gets cut, I need a backup.
Of course. Makes sense.
So you connect switch A to switch B, then B to C, and then to complete that backup path, you run a cable from C all the way back to A. You've made a circle.
And that, which feels like the smart, safe thing to do, it's actually the exact moment the whole network starts to just fall apart. You've made a loop.
You've made a loop. And that brings us right to why STP is so essential. Why is that loop such a guaranteed disaster?
Okay, yeah, let's break that down.
It all comes down to what we call the loop danger. And it's because of how the data packets at layer 2, the Ethernet frames, how they actually work.
Okay, I think I know where you're going with this. Unlike a packet on the internet.
Exactly. An IP packet, a layer 3 packet, it has a time to leave field. A TTL, it's like a self-destruct counter. After so many hops, it just dies.
So it can't get lost and circle around forever?
Right, but a layer 2 Ethernet frame, it has no safety mechanism like that, none at all. It's designed to stay local.
So if you send out a broadcast frame, one that's meant for every device on the network?
And it hits that loop you just created, the switches will just keep forwarding it endlessly. A receives it, sends it to B. B gets it, sends it to C. C gets it, sends it right back to A.
And then A gets its own message back and just sends it out again.
And again, but it's multiplying. The traffic is just exploding exponentially. And that unstoppable feedback is what we call a broadcast storm.
Wow.
Within just a few moments, the sheer amount of data, these endlessly looping frames, it completely overwhelms the switches. The CPU spike to 100%, the memory fills up, and the network just freezes.
So we're talking a total network meltdown. In seconds.
Literally seconds after you plug that last cable in.
Yeah.
It's that fast. That's the catastrophe that STP was built to prevent.
Okay, so its job is to stop the storm. It has to break the loop somehow, but without, telling you to unplug the redundant cable you just added for safety.
Precisely. Its role is simple in concept. It has to find one of those paths in the circle and just block it. It logically shuts down a port, turning that circle into a stable single line.
Logically blocked. So the cable's still there, ready to go if the main path fails.
It's waiting in the wings, yeah. Ready to be activated the second it's needed.
Okay, so the problem is clear, the job is clear, break the loop. But for all the switches to agree on which path to block, they first have to agree on who's in charge.
That's right. That brings us to the next part. Establishing order. Before any blocking can happen, you need a hierarchy. And the whole process starts with the switches talking to each other.
How do they talk?
They use these special little data packets. They're called Bridge Protocol Data Units, or BPDUs.
BPDUs.
Think of them as the ballots. They're the messages they send back and forth to run an election.
An election? Okay, so what are they voting on? What gives one switch power over another?
It all comes down to one thing, the bridge ID. Every single switch has one. It's like its name tag in the election.
And what makes up that bridge ID?
It's a combination of two numbers. First, there's a priority value, which an admin can set. And second, there's the switch's unique MC address, which is burned into the hardware.
I remember the sources mentioning that the priority value is almost always the same default number on every switch, right? Something like 32768.
Exactly. So in most real-world networks, because no one changes the default, all the switches start out with a tie on priority.
So how do you break the tie?
It falls back to the second part of the ID, the MBA address. And the rule is simple. The switch with the mathematically lowest MBA address wins the election.
That's fascinating. So it's not the biggest, most powerful switch. It's just the one with the lowest number for a hardware address.
It's a meritocracy of low numbers, yeah. And the winner of that silent election gets a special title. It becomes the root bridge.
The root bridge. The boss.
The boss. It's the ultimate point of reference for the entire network. Once that root bridge is chosen, every other switch on the network has one job.
Which is?
Calculate its best path to get to the root bridge. And it does this using a metric called cost.
Cost. So I'm guessing a faster connection has a lower cost.
You got it. The cost is based entirely on link speed. An old, slow 10 megabit link has a high cost, like 100. A modern gigabit Ethernet link, it has a really low cost of 4.
So every switch looks at all its possible connections and just adds up the numbers to find the lowest total cost to reach the root.
That's the entire logic. Find the single, cheapest path back to the boss, and once that path is identified, that's the one that stays active.
And any other path?
Yeah.
The ones that would create the loop?
STP blocks them, intentionally. The stability of the entire network depends on that election and the decision to not use those perfectly good backup cables.
Okay, the election is fast, the logic is sound. But the original old-school version of STP, it had a really big problem with timing. It couldn't just start working instantly.
No, it couldn't. And that moves us right into the next section, the cautious, slow nature of legacy STP. This thing was designed for guaranteed stability, not speed.
So when a switch boots up, it can't just start forwarding data.
Absolutely not. If it did, you could have a temporary disagreement about who the root is, and you'd get an instant loop. So it has to safely cycle through a series of states. 4 of them, to be exact.
Oh, it's the first one?
It starts in blocking. In this state, the port is totally shut down to user data. It's not sending anything, but it is listening to those BPDUs, those election ballots.
So it's listening to the election results. Then what?
Then it moves into the listening state. Now it's actively participating, trying to figure out its role. Is it on the best path to the root or not? But still, no user data, and it's not learning MP addresses yet. This state is timed.
How long?
15 seconds. It's a hard-coded timer called the forward delay.
15 seconds of just listening. Okay, what's next?
After that comes the learning state. Now the switch is confident about the network layout, and it starts building its MFC address table. It's learning where devices are. But to be safe, it still won't forward any actual data.
And I'm guessing that state is also timed.
Another 15 seconds. Same forward delay timer.
So we have 15 seconds of listening plus 15 seconds of learning. That's 30 seconds of delay already before a port can even start working.
30 seconds minimum.
Yeah.
And that's before you get to the final state, forwarding, where data can actually flow.
Right.
But it gets worse. There's another timer.
Oh, come on.
It's called the max age timer. It's usually 20 seconds. That's how long a switch will wait to hear from the root bridge before it decides the root is dead and a new election has to start.
So if the main path fails, a switch could wait up to 20 seconds and then spend another 30 seconds going through listening and learning before the backup path finally comes online.
You add it all up, and you're looking at a convergence time of up to 50 seconds. 50 seconds of a complete network outage.
An eternity. In modern terms, that's just completely unacceptable. Think about a voice over IP call or a database transaction. A 50-second outage is a disaster.
It is, and that's why legacy STP is obsolete. The safety logic was perfect, but the timing was a killer.
Which brings us to our last section, the necessary upgrade, the modern standard.
We're talking about Rapid Spanning Tree Protocol, RSTP, or, if you want its technical name, 802.1W.
And it does the same job, but faster.
Much, much faster. It uses the exact same core logic. Lowest bridge ID still wins. Cost is still the metric, but it completely re-engineers the timing.
How does it get around those 15-second delays? How can it be so sure it won't cause a loop?
It's just smarter. It's more proactive. RSTP introduces more detailed port roles. So a switch doesn't just have a blocked port. It might have what's called an alternate port. It already knows the port is the next best path to the root if the primary one fails.
Ah, so it has a plan B already calculated and waiting.
Exactly. And instead of passively waiting for timers to expire, the switches actively negotiate with each other. When a link comes up, a switch sends a sync proposal to his neighbor. They have a quick handshake, confirm that everything's loop-free, and they can bring the port up almost instantly.
So it's about consensus, not just patience.
Peer-to-peer verification. That's the key. And here's the bottom line, the number you really need to know. Legacy STP could take 50 seconds. Rapid STP, the 802.1W standard that runs basically every network today.
How fast is it?
It can detect a failure, switch over to that alternate port, and restore connectivity in less than 1 second.
Less than a second. That's the difference between a user not even noticing a blip and, an entire office grinding to a halt for a minute.
It is the technology that makes modern network resiliency possible. You just can't run modern services without that near-instant recovery.
So let's just recap this whole journey for you. We started with this silent killer, the broadcast storm. It's caused by layer 2 frames getting stuck in a loop with no way to die out.
And the solution was STP, which runs a little election. The winner is the switch with the lowest bridge ID, and it becomes the root bridge.
The boss. And everyone else just finds their cheapest path to the boss, and every other path gets blocked to prevent loops.
Right. But the old version was painfully slow, taking up to 50 seconds to fix a problem. The modern version, 802.1W, uses smarter negotiation to do the same job in under a second.
It really brings us back to this incredible kind of counterintuitive idea. The stability of our high-speed world rests on a simple election, followed by the intentional decision to turn off perfectly good connections.
And that really raises a final thought for you to consider. How often, in really complex systems, is the fastest and most stable solution found not by using everything you have all at once, but by intentionally holding something in reserve?
The value of limitation.
The value of intentional limitation. Blocking a port, in this case, is the secret to both speed and stability. It's a fascinating trade-off.
The silent election that's constantly saving your network from a storm you'll never see. That was the deep dive into Spanning Tree Protocol. We'll see you next time.